We are starting chapter 7 and 8. This used to be one chapter, and it's one chapter in most books, and they moved it to 2 in this one. So really the end of this presentation is really chapter 8, but it goes with what we're going to talk about in chapter 7. So just put it all together in one PowerPoint here. As for the exam, I added 10 points because I made a mistake in the answers on number 3. So the real answer wasn't there, so everybody got 10 extra points added in on that. I had, therefore, hundreds on there, and yeah, so there was 10 points added to your grade on Blackboard for that. That was my bad. Okay, so we're going to start talking about electrons and how they found well, we know how they found it based on, Thomson and that, but how they narrowed down the locations and how electrons move and things like that. Okay, so we got to talk about light. Okay, we're going to talk about the electromagnetic spectrum. Light energy is known as radiant energy. Okay, another type of energy that we have out there. And our electromagnetic energy, we have our first variable here, the speed of light, which is represented by c. All of our radiation move through a vacuum at the speed of light, which is 3.0 times 10 to the 8th meters per second. And they move in a wave-like fashion. So what is a wave-like fashion? Well, a wave-like fashion is the following. Okay. So here's what we got for a wave-like fashion here. All right, so let's take a look. We have a baseline. Okay. And we have something like that. Again, not drawn to scale, but this is essentially what we have. We call this here a crest. This is a trough. All right. And there's a couple things that we essentially want to measure. And I'm going to start the next wave like this. So here's our baseline. This is our baseline where the wave originates from. All right. The first thing is the distance between two crests. The distance between where one wave starts and then the next one starts is known as the wavelength. And it's a length, so it's measured in meters or some sort of metric unit of length. And it's represented by the Greek letter, which looks like an upside-down Y, lambda. Okay. Now, there's other parts of the wave we're not really going to get into. The distance from base to crest is known as amplitude. Okay. But we're going to focus on wavelength. Okay. So wavelength is represented by lambda, and all electromagnetic radiation, whether it's white light or X-rays or AM radio waves or microwaves, they all move in this this fashion. They all move in this fashion. Now, they all move at the speed of light, which is represented by c, 3.0 times 10 to the 8th meters per second, which is ridiculously fast. Okay. And we have another thing that we measure with our waves. We can measure the wavelength, and we can measure the frequency. Okay. Frequency is represented by the Greek letter nu. And if I could draw a good nu here. Something like that. It's kind of like a italicized slanted V. So this is lambda, this is nu. Okay. And what frequency measures is the number of waves in a given second. So how many full waves pass a point in a given second? Well, that means that wavelength is indirectly proportional to, or directly proportional to, 1 over the frequency. Meaning, As wavelength increases, frequency decreases, and vice versa. And it makes sense if you think about it. If I'm counting frequency, how many waves pass in a given second, okay, and I'm counting these crests in a given second, the shorter the distance between the crests, the more I'm going to count. So the shorter the wavelength, the more waves I'm going to be able to count. And the example I usually use is if I told you to stand at the edge of a road, and I'm going to have cars pass by, and I put the cars, 100 meters away from each other, and said count them over the next 10 minutes as they pass. And then we reset the experiment. Instead of being 100 meters apart, I now put them a meter apart. And I tell you, count the number of cars that pass in the given amount of time again. Well, you're going to count more cars when they're a meter apart than they are when they're 100 meters apart. So as wavelength goes down, frequency goes up. And as frequency goes down, wavelength goes up. So they're indirectly proportional with one another. Now, they are directly related to C in the following formula. C equals wavelength times frequency. We can manipulate this equation however you want to. Wavelength equals C over nu, or frequency equals C over lambda. Okay. Now, there's a couple things we have to take into account. Since we are basing it off of C, and C is in meters per second, in order to use this formula, my wavelength has to be in meters. My frequency has to be in 1 over seconds, or you'll see it written as seconds to the minus 1, which means the same thing, or that is known as hertz, or Hz. A hertz is a wave per second. Okay? So if something is 500 hertz frequency, that means there's 500 waves per second. So if you were given a problem where they gave you this in centimeters and this in kilohertz, you've got to convert it to hertz and you got to convert it to meters. Okay. But this is our formula, our first formula, and this chapter is going to deal with formulas. Okay. So, speed of light equals wavelength times frequency. C equals lambda times nu. So here's your first bad joke of this chapter. There's a couple. From now on, if someone asks you what's nu, you tell them C over lambda. If they get the joke, keep them in your life. If they don't, you don't need that negativity. You could cut them out. Okay, so this is the Greek letter N-U, nu. Someone asks you what's nu, you say speed of light over wavelength or C over lambda. They laugh, you're in the clear. They don't laugh, you don't need them. Okay? So if we were doing a problem here and we wanted to find the wavelength, what's the wavelength? And we are given a frequency of, let's say, 3,000 kilohertz. We would simply set it up. Wavelength equals 3.0 times 10 to the 8th meters per second over the frequency, which is 3,000 kilohertz, which is actually, we got to move the decimal 3 to the right. So add 3 more zeros, which is actually 3 million. Okay, and you can find that your wavelength is what? 1, 2, 3, 4, 5, 6. 3.0, or sorry, 1.0 times 10 to the second. Okay, and that would be in meters. because this is 1 over seconds, and cancel it out. That's okay, Mandy. You go and you find new friends. Maybe it's your awakening, your wake-up call during all of this. A new birth, a new beginning. Now you understand why I have a very limited friend pool that I pick from. Okay, questions on this? So I'm going to leave this formula here because we're going to need it. It's really plug and chug as long as you have the right... I'd have no friends, Mr. Coble. Oh, that's good stuff right there. You made me laugh. First person, I think, in my history ever to just say that. Mandy over here bragging that she's the smartest of her friends group. All right. So that's our first step. Okay, being able to take electromagnetic radiation. If I'm given a wavelength, I can find a frequency. If I'm given a frequency, I can find a wavelength. Okay. All right, and this is everything we just talked about. So our electromagnetic spectra, okay, range of frequencies and wavelengths of electromagnetic radiation. Where we're going to focus on is visible light. Okay, and visible light moves from a low energy to a high energy. And we'll talk about that and how you're going to be able to figure that out. Okay. But the colors of the rainbow are what makes up white light. So let's look at the electromagnetic spectra. Okay. We have things down here that have large wavelengths, which means they have shorter frequency. Now, here's what I need you to take away. All right? And we're going to talk about this in a couple minutes of how we actually calculate it. But if I increase my frequency, I've decreased my wavelength, I increase my energy. Energy and frequency are directly correlated to one another. Similar, decrease my frequency, increase my wavelength, decrease my energy. So the longer the wavelength, the lower the frequency, the lower the energy. Okay. So if we look at the spectrum, we've got AM radio waves. Way down here. We have gamma rays way up here. Okay? So, if we go this direction, it's actually not a bad arrow being drawn with the mouse. If we go in this direction, we're increasing our wavelength, which means we're decreasing our frequency, which means, we're decreasing our wavelength. I'm increasing going this way. Let me erase this real quick. I'm going backwards. I'm actually talking and looking at it left to right and drawing it. I'm speaking of it right to left and talking about it left to right. Okay, let's erase these arrows. As I move in, I just like playing with the eraser on here, to be honest. All right, as I move in this way, my wavelength is decreasing. It's getting smaller. It's going from 10 to the 4th to 10 to the minus 15th. Therefore, my frequency is increasing. Therefore, the amount of energy that the wave is presenting, okay, is greater. So a gamma ray has greater energy than an AM radio wave, which makes sense, all right, because X-rays, gamma rays, ultraviolet rays are what does damage to us. AM radio waves, unless we're sitting right next to the tower or something like that, we're not really going to get injured. Okay. Look at our visible light. Okay, this is the wavelength in nanometers. 400 nanometers to 700 nanometers. Okay, going in this direction. Okay. So if I go back 2 slides here, go back 2 slides. Violet, all right, is going to be high energy. Red is going to be low energy. Well, how do I know that? Okay, so I go this way, drawing our little arrow here. If I go that way, what's happening? My wavelength is increasing. Therefore, my frequency is decreasing. Therefore, my energy is decreasing. Now, I don't expect you to know exactly where each color is, but we all know that the colors of the rainbow go Roy G. Biv. I expect that you know that red is my largest wavelength and lowest energy, and purple is my lowest wavelength and my highest energy. And then everything else falls in between. So if I asked you to compare green to violet based on wavelength, you should know that, by Roy G. Biv, green has a larger wavelength. Green also has a lower frequency. Therefore, green has a lower energy compared to purple. Okay? Which puts us to an interesting thing. That means that all the colors we see, all the white light that we come around, AM radio waves, FM radio waves, going to get an X-ray, I should say, laying out and having sunlight hit us, ultraviolet light, all have some form of energy. Speaking of which, I always talk about here why we see the colors that we do. Okay, first of all, we see rainbows. We see rainbows if there's moisture in the air because it acts like a prism and it separates our white light into its primary colors here, into its color stream, continuous stream of color. Realize that there's no dark spots in the rainbow. Red blends to orange, orange blends to yellow, yellow to green, green to blue, and so on. Okay. Also, for a rainbow to be seen, the moisture in the air, the sun has to be at a specific angle, so you can only see rainbows at certain times of the day when the sun hits the moisture droplets at the correct angle to separate that light. That's another interesting thing. But why do we see the colors that we do? Okay, which leads us to a different perspective on what is reality, at least in my opinion. So, okay, everybody sit back, okay? Everybody, we'll take a puff and we'll pass it around here as we, if that's your thing. If it's not your thing, if you have a medical card and it's your thing, do it. But let's talk about seeing colors and things like that and how it's a perception of your reality. In order to see colors, you need light to reflect off of. So my shorts are orange with some black on them. Okay, my shirt is a blue color. That's red up on the board. That's a different shade of blue up on the board. Isn't it funny though, Rob? Like the meme says that the Pentagon drops that UFOs have existed for a while and no one really cares. It's like they waited for this to drop that. But anyway, that's another time. So color is a perception of how you perceive the light reflecting off of it. So why do I see this as red? Why do I see this as blue, this is orange, this is black? The first thing is you need light. Light is, or color is a reflection of light. Because if the room is completely dark, you can't see anything. So every object you see, and for that matter, and we're not talking about sound here, but we're talking about light. Every sound that you hear is a reflection of the sound. So you're not seeing the color directly. You're not hearing my voice directly. You're hearing my voice, reflect off something, bounce off something, and go to your ear to be perceived. So why do you see red? Well, white light shines off of this, absorbs all the colors except this one that you see, which is sent back to your eye. Your eye then, in a split second, sends the signal, processes it, sends it the signal to the brain, and the brain spits back, that's red, or that's rojo. I only know Spanish. I can't go French or German or anything for red. Why do I see orange? Because the same thing is happening. The white light is being absorbed. The light that's reflecting back is orange, and I'm seeing that. But my brain is processing that as orange, and my brain is processing that as blue. And my brain is processing that as red. So in my reality, this is red. But that's only in your reality, or my reality, or we're sharing the reality that's red. But what if you have red-green color blindness? And your brain or your eyes are missing the receptors, and I'm not going to get into rods and cones, we'll let biology do that, but your receptors don't pick up that that's red. Maybe that looks gray to you. Then in your reality, that's gray, because that's the way you are processing that reflection of light. It's just a giant reflection. So everything you witness, everything you perceive, everything you're looking at, and I know I'm getting metaphysical here in a chemistry class, but everything you perceive, and this is why I miss being in the classroom with you guys, all of that you see is just your interpretation of what you see. And if you don't believe me, go back into the whole, Yanni thing that was on Facebook, that you could hear Yanni or Yarny or whatever it was, or the blue and the gold dress. Some of us saw blue, some of us saw gold. The sneaker, where some saw green, some saw pink. So what you're saying is a reality is your reality, but it's not necessarily someone else's reality. It's your reality on how your mind is perceiving what you are witnessing based on the interpretations and signals that are being sent back to you. Now, is that what chemistry is doing? Well, no. In chemistry, we have a machine. We have a machine that'll measure this wavelength, and we'll place it onto that electromagnetic spectra and say, yes, this is red. But you'll say, no, I'm seeing, green, or I'm seeing gray. Well, no. If we run it in a spectra and we see what the wavelength is, we can physically tell you what color that is. What I'm saying is the human mind and your experience is just a manifestation of actual reality to make it your reality. I know, that's ridiculous, right? So when they tell you wearing white after Labor Day is a fashion faux pas, it has nothing to do with fashion and everything to do with science. Before Labor Day, it's summer, it's hot out. You want to wear white. Why? White, when the light reflects off, it's going to reflect everything back to your eye and you're going to perceive it as white. You don't want to wear black because the black will absorb all the white light energy, making you hotter. And what's being reflected back to the eye? Nothing, because it's being all absorbed by the black shirt. Now, after Labor Day, it's supposed to turn to fall. It's supposed to get cooler. Don't wear white because now we want to harness the sun's energy. We want to harness that white light. We want to stay warmer. So wear dark colors, get rid of white. How's that? Any comments on that? Anything you want to discuss further on that? So why you're seeing the colors that you do is a reflection of the light that's reflecting off of it, coming back to your eye, whatever it's not absorbing. Your mind processes it and tells you it's that color. Now think about that. If I drop this right in front of the camera right now and say color, all of you looking at this, all 9 of you watching the video right now, say blue or purple, right? So all of you say blue or purple, and you did that in a split second, right? I hold up this tape here, and you say that tape holder is black, and you know that in an instant. That's how fast that process works. That's how fast that light reflects off of that, sends that signal back to you, and your brain processes it for you to say the words black, red, blue, green, purple. Like, if that just doesn't amaze you, all right, and make you sit back and realize again how really insignificant we are in the grand scheme of things. I'm not saying, again, you as a human are insignificant and whatever. I'm just saying, in the grand scheme of things, what's going on behind the scenes, you know, our mundane everyday lives are just... like, that's crazy. Because if I shut the light off in here... that might change the shades. I shut my computer screens off, make it even darker, then I drop this in front of it. Maybe that doesn't look blue anymore. Maybe in your mind that looks like a different color. You change the light bulbs from, you know, regular watt light bulbs to fluorescent lights, or yellow lights, or green lights, or a black light. And think about what pops up. Okay. So the question is, why is the sky blue? What's our answer? Well, the sky is blue because when the light coming through, all right, what's being scattered and what's being absorbed and what's reaching our eye, stuff's being scattered, and the wavelength that's predominantly coming to our eye is blue light. Is that color blue in that 450 nanometer range? And our mind processes it. Our eyes process it, send it to our mind to process and spit that back out. If you love sunsets and the different colors of the sunsets, and my wife gets ticked off at me all the time and says, I just can't appreciate things. And I say, well, I appreciate them a little bit different. But if you like sunsets, oh, the purples and the reds and the oranges, and look at how great that is. Well, the angle of the sun is hitting dust, dirt, smog, pollution, and everything else that's going around, scattering the light, making us see those colors. So yes, sunsets are beautiful, as pollution and dust and dirt is beautiful. And that's what I'll say. She'll be like, look at all those cool colors. Isn't that beautiful? And I'll be like, yes, pollution and dust and dirt are beautiful. And she'll be like, you have to ruin everything. Okay. So think about all the fun. How is that depressing, Kelsey? That's not depressing. See, you gotta be, I'm the pessimist of the group here. I am the ultimate pessimist. But that's the beauty of it. Oh, I'm a thrill, buddy. Rob. That's why I said, after all this, me and my wife being stuck in the house together, if we end up getting divorced, I'm never getting married or involved ever again, probably, because my pickup lines are this. Would you like to discuss why your beer is yellow? Would you like to discuss why your vodka cranberry is red? And let me tell you about how that alcohol be digested in your body. What's up? Okay. That's my wife getting ready to divorce me to come on in here. Oh, yeah, it would work. It would definitely work, Trent. Let me tell you, it worked for the, 24 years before I met my wife. It worked real well. But anyway, back from my dating life as a college student to this. Now when you're out, think about all the fun you can have. If you know the wavelength of the color of the object that you're seeing, you could calculate its frequency. All right, so much fun. Now, your idea of fun and mine might be a little bit different. So let's go on to the next slide here. And it's a problem. And I'll let you do the problem for homework. So sample problem 7.1 you could do for homework. But look at this, okay? So let's say you go to the dentist to get a cleaning and they do an x-ray. It says a dental hygienist uses x-rays that have a certain wavelength, 1.00, A with a hat. Now, I'll tell you this. A with a hat is known as an angstrom, and it's equivalent to 10 to the minus 10th of a meter. Okay, so an angstrom is 10 to the minus 10th of a meter. Mandy, so much fun. It is, I'm telling you. It's a blast. All right. So, you guys. All right. They have a radio station on with a wavelength of 325 centimeters. And you look out the window at a blue sky, which has 473 nanometers. It says, what is the frequency? So they want you to calculate nu. They want you to use this formula right here to calculate nu for each one of these. The key to this problem, and that's going to be a big key this whole entire chapter. All right. The key is make sure you get these into meters. All right. Notice that they're in nanometers, centimeters, and angstroms. Now I want to point out this whole radiographs, okay, and then they talk about that's your X-rays. I already talked about angstroms, and then the radio station. Now, before satellite radio, before you guys gave up on regular radio, and I don't blame you to listen to Spotify or Pandora or Amazon Music or whatever it is, you used to actually have to tune into a radio station, where you had to actually turn the dial. You had to, instead of push a button and put the numbers in, you actually had to find the radio station. And there was two choices, and there still are, AM and FM. Okay. And your AM stations might be something like 6:30 AM. And I don't know, what do we got? Froggy 101, 101.3, or we got 98.5, or 97.9. Okay, I think it's still in the area. I don't know. I'm one of the ones that changed and went to satellite radio. What are these channels that you're tuning into? The only reason you guys are having fun is because you have 1 week to go. What are these? What these are frequencies. These are news. Okay. The AM is measured in kilohertz. FM is measured in megahertz. Now, a megahertz is 10 to the 6th of a hertz. Kilo, is 10 to the 3rd and moving the decimal place. So, think about all the fun you could have now in your car. Listen to this one. You're driving your car, you're listening to, I don't know, what do you want to listen to? 98.5 sounds good. We'll listen to KRZ. So we're listening to 98.5. You're driving in your car and you stop at a red light. Now, the light is red. You know red is around 740 nanometers. So from that, you could figure out what is the frequency that you're seeing that red light at. Right? That's crazy. Then, while you're sitting there, you say, boy, I'm listening to 98.5 megahertz. I can calculate the hertz and then calculate the wavelength. Geez, all the fun you could have. It's a blast at parties. If anybody asks for a new party game, tell them go around and pick out a color and figure out the wavelength. All right. Okay, any questions on how to find the wavelength or the frequency using that C equals lambda nu formula? Just please make sure you're in the correct units. If you're not in the right units, since C is in the correct units, all right, since C is in meters per second, you have to make sure you're in hertz. And you have to make sure you are in meters for your wavelength to have this work out. So any questions on that right now? Questions, questions, questions. Because I want to get to one point today in this chapter. We'll see how far we get. All right, we're good to roll then? Cool beans. All right, so again, try this sample problem for homework because it's there, the answers, and I'll assign a couple more out of the book. We don't have to talk about cell phones. They aren't dangerous. Are microwaves dangerous? They're not dangerous either. Their electromagnetic spectra falls down between FM and AM radio waves, so we should be okay. That doesn't mean to expose yourself to large amounts of microwaves. I had a student once tell me that, I talked about microwaves and saying that microwave ovens, microwave ovens, they thought people were going to go sterile and get cancer from using them. But I had one person tell me that their sister studies microwaves and they said I was a liar. And they meant actual studying of microwaves, not the microwave ovens. I was talking about ovens. And yes, if you're going to be exposed to microwaves 40 hours a week for the next 40 years of your life, yeah, you should take precautions. But let's talk about this guy here, Max Planck. Okay. Right. So, Planck needed to, or what he theorized in, was that the energy that the light that is being absorbed and reflected all essentially come off in increments he called quantum. Basically, what his formula does, this E equals h nu, that's right here, okay? What this does is allows us to, all right, allows us, E equals h nu, to find the energy based on the frequency. So here's our second formula. Now, h is known as Planck's constant. It has a value of 6.626 times 10 to the negative 34th. Now, don't confuse that with Avogadro's number. People do that all the time. Don't. Okay. So here's our second formula. Okay. It's a way to relate frequency, once you know it, to get the energy. Okay. E equals h times nu, where h is 6.626 times 10 to the negative 34th joule times seconds. Okay. Now, what your book does is a two-step thing, and I want to show you. I learned it and kept it this way and did the problem in two steps. What your book does is it takes E equals h nu, right? And it solves it for nu. It says nu equals E over h, the energy over Planck's constant. Then they take this formula down here and say nu equals C over lambda. Okay, whoops, wrong color here. C over lambda. And they basically plug the two into one another. Okay, so they say, all right, well, if that's the case, then C equals lambda nu. And I'm going to plug this in here, so they write the formula out as C, they take both formulas and write it out as C equals lambda times E over H. And they make a combination formula like so. You don't have to do that. I'm just showing you your book does that. You could solve for a frequency here, then plug it in here, and do it in two separate motions. Okay. The key, though, to this E equals H nu stuff is this right here. I can't have half values. I can't have increments. So what I mean by that, all right, they have to be whole number increments of whatever H nu is. So if I calculate H nu for a specific electron or something like that to be 5, there can never be a value for that specific substance as 7 or 8 or 11 or 13 or 19 or 24. If I calculate E to be a value, the next value has to be double that, or triple that, or 4 times that. It has to be a multiple of whatever H nu is. And the way to think about it is walking up steps. And I know that sounds silly, but if all the steps are made correctly, and let's say it takes 1,000 joules, again, making up numbers and just making round numbers to make it, 1,000 joules to get from the base to the first step. How many joules is it going to take to get to the second step from the base? Another 1,000 joules from the first step to the second, or 2,000 total. To the third step, another 1,000, or 3,000 total from the bottom. From 3 to 4, 1,000, or 4,000 total. Multiples. Well, if I put in 2,500 joules of energy, I can't get to that third step. I can get to step 2, but I can't get to that next level. And that's what Planck's constant is saying. That these energy, these light energy molecules, these things we're looking at and seeing and observing, move to different and higher energy levels. And since they move to different and higher energy levels, they need a certain amount of energy to reach each energy level. And if that energy isn't achieved, then we don't reach that level. If it takes 1,000 joules to get up one step, and I want to walk up a flight of 10 steps, I got to put in 10,000 joules of energy. 1,000 each step. If I don't, I'll never reach the top. And that's what Planck's constant's saying. If you want to move from level 1 to level 2, you got to put in the same amount of energy. Okay. Now, this was Planck's theory. It needed to be proven. Okay, and you could try 7.2 for homework. That's basically calculating the energy given wavelength and frequency and stuff like that, and finding the frequency, and you could do it 2 ways. Again, they give you this formula, E equals hc over lambda. They're just combining the formula that I showed you. They're combining the two and manipulating it, but you can do it. So, Einstein in the early 1900s goes out to prove the photoelectric effect. And that is the idea of Planck's constant equals the frequency, and it has to move up in whole number ratios. Here's what he did. Okay? Here's what he did. And I have, there's Einstein, right here. He took some light-sensitive, photosensitive plate, metal plate, and he bombarded it with light. And here it is. Here's light. Anytime you see H nu, okay, let's say over an arrow in a reaction or something like that, it means that light was used. So he bombarded it with light in a vacuum, and he bombarded it with a certain wavelength, okay, which has a certain frequency, which then would have a certain energy based on H nu. He would measure electrons coming off by a current meter, an amp meter, looking for electrons, because that's all it is. And what he found was this. He had to reach some threshold value for the electrons to come off. That the incoming light's H nu value, had to be of a specific value for the electrons to fly off. If it was of a lower value, nothing happened. If it was of a greater value, we've already reached the threshold and the electrons fly off. Which means that my electrons are sitting in a certain spot that need a certain amount of energy to release them. So what this does is proves Planck's constant, Planck's theory, Planck's idea that E equals H nu. What it also does is states that, our metals and our electrons must be sitting in different areas depending on what it is, because it's going to take a certain amount of energy to release electrons from, let's say, gold than it is from sodium. So we start looking at and knowing, hey, we have electrons and we kind of know where they are, but we now start realizing that the electrons, and remember, 1905, if we go back, they're studying this. Thomson has just come out and said electrons are in everything. Millikan is working on, while Einstein's doing this stuff, Millikan's working on doing the oil drop experiment. It's not until, let's say, 15, years later, roughly, that Rutherford discovers that the electrons are on the outside. So all of this is going on together. They're not working together, but all of this research and data collection is going on together about how are our atoms arranged, what is going on with light, what are these electron things, and so on. Okay, so he calls them photons. All right, photons are also known as quantum. But see, here is the problem then. Is light a wave or is it a particle? So by a wave, does it have a crest and a wavelength and all of that fun stuff? A frequency? Or, since you're telling me it's made of electrons and we later find out that electrons have mass, then if it has mass, then it's a particle. Well, the thing is, light acts like both. Light acts like a wave and it acts like a particle. On the big scope, it's a wave. But on the tiny scope, what's making that wave? Electrons, which is a particle. Okay. And this is just showing the difference. And I mean, the way I explain it usually in a classroom is, if you have a flashlight, okay, and you shine the flashlight on the wall, you see the big circle on the wall, and you see the little tiny beam circle in the middle. Now, this isn't exactly quantum physics, but it'll give you the general idea. If I walk closer or I walk further apart, the wavelength part gets bigger or smaller depending on my distance from the wall. However, that middle, that kind of looks like a ghost, all right, that middle of the flashlight, that beam, that doesn't change its location. And that in turn is the beam particles, the beam of particles coming through that they're talking about here. While the wave is the thing that is spreading out and making the circle bigger further away or smaller as you get closer. So light has both wave, has a frequency, has a wavelength, therefore has an energy, but it also has a mass. Now, I don't mean that if I take an empty box and I zero out the balance and I put the box and zero out the balance and there's zero, and I take a flashlight and I shine the light into the box, that it'll read mass. But mathematically, since it's made of electrons, light has a mass because it is a particle. Okay. Questions on that? Because I think that's a good place to stop. I've already depressed Kelsey. Some of you, I gave you things to think about while you're relaxing. I just used air quotes. Relaxing over the weekend. So let's find homework on this. The couple of sample problems on the slides. Okay, so sample problem, I think it was 7.1 and 7.2 on the slides. Okay, on the slides. And then in the book, let's take a look. Ooh, look at that. I'm a poet and I don't know it. All right, we're on page 325. (7.1) and 7.2. (7.7 to 7.14). 7.7 to 7.14. All right, so sample problem 7.1 and 7.2 on the slides. Page 325, 7.1 and 7.2. 7.7 and 7.14. Okay. All right.